Let's do section 11.1, page 553, exercise 48, which reads, a particle moves in the plane so that its position at any time t, 0 less than or equal to t less than or equal to 2 pi, is given parametrically by x equals sine t and y equals cosine 2t. Part A asks us to find the velocity vector for the particle. Well, let's start by reminding ourselves that the position vector is equal to x comma y, and in this case that is going to be equal to sine t comma cosine 2t. And then we know, because we just talked about it, that the velocity vector is going to be the derivative of the position vector. And we're going to take these derivatives of each component independently because we treat the x and the y directions separately. So we're going to take the derivative of sine t with respect to time and get cosine t, and then we're going to take the derivative of cosine 2t with respect to time and get negative 2 sine 2t. So this is going to be our velocity vector. Part B asks us for what values of t is the particle at rest. Well, if the particle is at rest, that tells us that its speed, which is the magnitude of the velocity vector, has to be equal to 0. And we know how to express that speed. It's going to be the square root of the sum of the squares of these components of our velocity vector. So it's going to be cosine t squared plus negative 2 sine 2t squared, and we take the square root of that sum, and we want it to be equal to 0. And if I square both sides to get rid of that radical sign, I'm going to have cosine t plus 4 sine squared 2t has to be equal to 0. And by looking at that, I can see that this is really only going to happen when t is equal to pi over 2 and 3 pi over 2. All right. Part C says, write an equation for the path of the particle in terms of x and y that does not involve trigonometric functions. So basically, we want to find y in terms of x, which means that we've got to eliminate our parameter t. And let's just remember that x is equal to sine t, and that y is equal to cosine 2t. Now I'm expecting that the fact that I've got different arguments in my trig functions might cause a little bit of a trouble, and perhaps a trig identity is going to be helpful. So let's start by remembering what cosine 2t is equal to. And if you look it up in your book, it's equal to cosine squared t minus sine squared t. Now this is getting us somewhere because I've got cosine 2t, that's y. Sine t is equal to x, so sine squared t is going to be x squared, but I still have this problem because I've got a cosine t. So maybe I'm going to need another trig identity, a trig identity that's going to relate cosine squared t and sine squared t. Well, everybody's favorite trig identity is cosine squared t plus sine squared t is going to be equal to 1, which means I can say that cosine squared t is going to be 1 minus sine squared t. And I can substitute in. So I'm going to have cosine 2t is going to be 1 minus sine squared t minus sine squared t. Or cosine 2t is going to be 1 minus 2 sine squared t. And then I can go back up to my original expressions here and see that cosine 2t is going to be y, and that sine t is going to be x. So I end up with y is equal to 1 minus 2x squared. The last part of this problem asks us to sketch the path of the particle, and you can either use the parametric mode on your calculator and use the original equations, or you can use your answer to part C. And when we do that, we've got a parabola that's concave down, that's centered at the origin. And so that will be the path of the particle.